Welcome to my presentation today, comparing two technologies for solid phase peptide synthesis. One what we call stirred bed technology and the fixed bed continuous flow technology that everyone knows. I will compare both technologies, provide some information on challenges, the process and continuous improvements that we have done for this development, and I will provide some case studies where we really applied that technology for making therapeutic oligonucleotides. So as hopefully someone of you knows also that Bachem originally is working on peptides. So we have a lot of experience since decades using stirred bed reactors because that's the state-of-the-art technology for manufacturing of peptides. So the idea came up, can we use that kind of reactor technology also to manufacture oligonucleotides? That's obviously not a new idea. Back to the 1980s, there were already some DNA synthesizers applying this technology. But as you know, over the last decades, the continuous flow fixed bed synthesis has established as standard. One of the drawbacks of the current continuous flow through technology is some inhomogeneity that you observe if you perform sample cleavages with samples taken top and bottom of a column. So you see different impurity profiles, and by definition, a stirred bed reactor gives a better batch homogeneity than the current standard technology. So as we began this journey, the first milestone was to demonstrate feasibility of this new concept. As this was done, we started to work on generic platform conditions that we can use for each sequence as starting point for process development while maintaining purity and impurity profile compared to the standard continuous flow technology. And finally, we are focusing on reduction of the process mass intensity, mainly to save solvents, and with the overall goal to be ready to manufacture oligos up to metric ton scale. As you all know, SPRS is a standard technology for synthesis of oligonucleotides, standard phosphorus-3 chemistry. It's optimized for short cycle times and high throughput. It's a well-established and well-known technology, and it's highly repetitive. So we decided also that we want to not go away from this general technology concept and use this also for our stirred bed technology. Let's compare both technologies. So on the left, you see the continuous flow fixed bed synthesizers that has some disadvantages, especially a limited scalability. I will provide later on some more insights on that. It's strongly depending on bed height and flow rates, and strong resin swelling will not be tolerated. In contrast to that, our stirred bed technology has a very good scalability. It has an independency of the bed height and flow rates, and we can also work with swelling soil supports. Let's have a closer look on the equipment. So on the left side, you see typical peptide reactors. On the top sits a medium scale synthesizer, 75 liter, that we can use for peptide synthesis in the low mole range. For oligonucleotides, we have comparable equipment that you know all from Asahi, Cytiva, also in the same range around a few mole scale. Going to our large-scale equipment for the peptide synthesis, meaning 1,000 liter reactor, where we are able to manufacture up to 35 mole in one batch, there is no comparable equipment at the moment for synthesis of oligonucleotides. And that is the gap that we want to close with our stirred bed technology. So our goal was to keep, in general, the concept for solid phase oligonucleotide synthesis, phosphorus-3 chemistry, common activators like tetrazoles, typical building blocks that you all know, polystyrene-based supports. So overall, mainly the same starting materials and chemistry as the continuous flow synthesis. But of course, we had to adopt something. So let's have a closer look on the detritylation. So detritylation is a very fast reaction, but it's coming with a competing side reaction, the depurination, which can lead to abasic impurities or even chain termination. So it's important to keep both reactions and the ratio of each in mind, to work on a question like how we can adjust the titration conditions. So that's especially important as we have this step in each cycle, and we need to control this formation of site impurities to have at the end an overall good quality and impurity profile comparable to the standard technology. So we optimized the synthesis protocol for the detitylation in stirred bed reactors, and that required some chemical and engineering adaptation of the current processes. To test the detitylation, we used the generic ale-rich DNA sequence, performed the standard detitylation using DCA, and ended up with a very low purity and a typical impurity profile, including depurination. So in general, it was possible to use the standard detitylation reagents, but the quality was not very high, and some good synthesis protocol. So we went in a deep dive into detitylation chemistry. We screened different reagents to come away from the standard DCA. And here you see one example of the detitylation cocktails that we have evaluated. In this example, it's shown that we use cyanopyridine TFA salt combined with fluorinated alcohol. So we are still using taurine, a standard solvent, and we are adding a scavenger, DODT, to trap the detrial cation. We performed now again the detitylation for the previously shown A-rich DNA sequence and ended up with a much higher purity of 78%, which is comparable to the standard protocols for the continuous flow synthesis. So that was very promising, and we went further into optimization of this technology. So here you can see that also scale-up was very well done. On the left side, you see a 1-liter reactor that we typically use in process development in my labs, and we performed a scale-up into a 75-liter reactor, and that gave also very nice results. We will see that as well on some following slides. In the meanwhile, we have done several hundred syntheses using our new protocol. And I will show you now 3 different case studi' mainly related to siRNA sequences. First one is in 23rd MER with standard 2' modifications and partially modified. Second one as well. And we have a third case study dealing with a fragment approach. So have a look on the first case study that shows also some of the history for our process development. The baseline experiment is always in standard continuous flow synthesis. Here it's done on an OP100. We achieved a purity of 75%. And then we have applied our generic conditions, ended up with close to 60%. And we have done some iterative optimization studies to enhance our generic protocols. And we finally ended up with a very comparable purity of 76% and also a very comparable impurity profile. For the next case study, we applied our generic conditions and performed also some process optimization, ending up with an even better impurity profile compared to the standard protocol applying 10% DCA for the detitylation. So we have a very good and comparable purity and impurity profile applying our new technology and new detitylation cocktail. We can apply our stirred bed technology also for synthesis of short fragments that can be used for chemical or enzymatic ligation later on. Here you see that we ended up for short 8 MER with above 90% purity after cleavage and deprotection. After having completed also the TFF step, we end up close to 97%. So overall, very nice and promising results. And we could show that this is also applicable for a fragment approach without purification of the fragments. So we can use these fragments as crude material after TFF. As mentioned before, we did also some scale-up studies. Here is one example shown from a 10 milliliter reactor, 40 micromole scale, to a 75-liter GMP-qualified reactor with a 300 millimole scale. As you see here, it was a very short sequence, only in 5 mol DNA, but it was only a proof of concept to demonstrate that we are able to scale up our technology, and that was very successful. And we had, by this work, also optimized our equipment to be able to manufacture larger quantities applying our new technology. Besides the equipment that we have already in place for process development, we are adding some more capacity in this year for process development that will be installed in the next few months. We are working also on a pilot scale synthesizer that is ready for GMP manufacturing and non-GMP manufacturing up to 500 gram batch scale. This equipment will be also available in this year. And in our new manufacturing building K, where we install our large continuous flow line, we are adding one more line with stirred bed technology, enabling us to manufacture at the end up to metric ton scale, depending on the sequences and process. And that equipment will be operational from 2025 on. So as we have a lot of experience from peptide manufacturing and CMC activities of peptides, where we used extensively the stirred bed reactor technology, we have a similar approach. So usually we start with a feasibility study based on our generic platform conditions on a parallel and fully automated synthesizer. For some process optimization studies that are specific for the sequence, we use the same equipment but increase slightly the scale to 200 micromole to perform optimization studies to reduce the PMI, washing volumes, reaction times, and so on. We then end up typically in our lab work with a scale-up, for example, in a 1 liter reactor system, meaning it's a scale of 5 millimole. And after that, we have demonstrated the proof of concept and applicability of that process, and we can transfer it to our large-scale or small-scale GMP equipment, going towards mole scale at the end, depending on the equipment. So I've shown you now that we are able to increase our output for the synthesis of oligonucleotides, but to have an overall manufacturing process that is able to deliver metric ton scale, we have to match that with our downstream capacity. And that's where our MGS-GP systems come into place. Bachem is proud that we have the first GMP large-scale systems for continuous purification of peptides, but as well for oligonucleotides, and we have also there some nice results. We performed several process developments on continuous oligochromatography, and applying these technology together with the stirred bed technology, we are able to achieve output at metric ton scale. Now some words from an industry perspective and scaling equations. If we have a look on the standard batch size, so for the continuous flow system, it's around 2 mole per batch. And if we compare that with a typical system for the stirred bed synthesis, that would be a 75-liter reactor, where we are at the same scale, then obviously we are not ending up with a benefit because we have to manufacture the same number of batches to end up, for example, with 70 mole. But as I've shown before, we can easily scale up for the stirred bed technology. So going towards larger equipment, for example, 1,000-liter reactor or even 3,500-liter reactors, we can increase dramatically the batch size up to 70 mole in one batch if we want to. I'm not telling you that this is a good idea to manufacture 70 mole only in one batch, but in general, this could be feasible. But we have overall for the stirred bed technology the benefit that we can decrease the number of batches that we need to manufacture to achieve an output at 100 kilogram up to metric ton scale. So one typical industrial use case for APIs that require large amounts per year is the combination of a fragment or chemical ligation with the manufacturing of fragments by applying our stirred bed technology. You not need any purification steps of the fragments. You can work with the crude material for the ligation We can tolerate green solvents, and with that we have a very good process efficiency for manufacturing large quantities of oligo APIs. Overall, some more considerations from an industrial perspective. We have still the standard coupling chemistry that we apply. We have to optimize the distillation cocktail. I have shown the results for that. We are manufacturing homogeneous material by definition of that technology. We can tolerate highly substituted supports. We can use swellable supports. We can perform on-resin modifications directly in our reactors. And we can combine this technology, as shown before, with a continuous chromatography and end up with a really efficient manufacturing process. Some last words on process mass intensity, which is an important KPI to have a look on solvent consumption. So comparing the standard flow-through synthesis and our unoptimized still bed conditions, we are at the same range. After thorough optimization of our conditions, we are ending up with a lower PMI. And at the moment, we are working on the application of higher loaded supports, which would give us even lower PMI values as we expect. So overall, we are assuming that we can achieve a 50% reduction of the PMI comparing to our standard continuous flow synthesis conditions. So let me briefly summarize my talk. I am again comparing both technologies. So fixed bed synthesis comes with some advantages. It's a well-known, well-established technology in chemistry. It's a very fast chemistry, short cycle times. Everybody knows the synthesizers available from small scale to large scale, but it comes also with some disadvantages. We are manufacturing partially inhomogeneous material. We have a limited scalability, mainly depending on the size of the pump skid that we would use, while the stirred bed technology comes with some advantages. We are manufacturing homogeneous material. We can tolerate swelling of the resin. We can use highly loaded supports. We have a very good scalability. We can work with on-resin modifications, and we can save solvent consumption, so meaning reducing the PMI. And with that, I'm already at the end of my talk and open for questions now or even later on at our booth. Thank you, and I'm open for questions.
First, thank you, because I've waited years for somebody to do this experiment, okay? But I guess one of the advantages of a packed bed is that it drives the products out of the reaction milieu. In other words, helps drive things to equilibrium. So I was wondering if that might be an impact of your much more aggressive detritylation cocktail requirements than we typically would use in a packed bed. Comment?
So yeah, it's important that we use a scavenger to have an influence on the equilibrium because we have also to adopt the reaction times for our technology, as we have filtration times in these reactors, and that requires more time compared to the flow-through systems.
Okay. The other thing that would be interesting, has always been, is heat of reaction. You, in your detritylation, what sort of heats of reaction do you observe? For example, how much delta T do we get out of those?
We haven't investigated so far.
Okay,
so
but is there one? I mean, I assume you have a thermocouple.
From our lab experience, we see there are no issue, but in general, we have temperature-controlled reactors also that we could apply if we would have an issue with that. So we have double-jacketed reactors with full temperature control available for that technology as well.
Okay. Is there a crossover point at which one technology works better than the other that you established?
So our thinking is that this technology at the moment is especially interested for people who requires large amounts of oligo APIs. Because also referring to customer discussions that we had already, authorities or the customer knows, of course, continuous flow synthesis, but no one knows stirred bed technology. And with that, there are assumptions how big is the risk also when you go into filing of a process applying stirred bed technology. And we see the huge benefit for large quantities at the moment. But of course, we can apply it also for small quantities. We have the equipment ready for that. There could be a combination of both. That is something we are looking in. In general, we are still working on that technology to have further improvements, and that is one of the interesting directions.
Very good.
Hi, I'm here. Nice summary. Two short questions. First, related to detutelation. You have a new system for detutelation, and I would imagine that that would also work on a fixed bed reactor. So the question here is that, have you tried your system on a conventional fixed bed reactor, and does it work?
It's the same answer as 1 minute ago. So
Right.
yes, that could work, and that's something we are still looking into it. So we are still working on this whole technology, and if we have a combination of our detutelation technology with the standard technology, so that should be in general applicable. Yes.
Okay, so just connected, this question or follow-on would be, how long is the detutelation step with the new system now?
So it's longer compared to the standard
How long?
process.
How many minutes?
I will not comment on that.
Okay.
But the overall cycle times are longer. But if we are talking about large-scale manufacturing, then this doesn't play a role. So it's longer, but it's not that we have to apply 1 hour or something like that.
Sure.
But I cannot comment on,
All right,
on more
understand.
details.
And then second question is about the polystyrene support, which you mentioned. And in our hands, we have seen that the polystyrene bead is very difficult to really mix it. It always floats. So the contact is very difficult with the reagents during the stirred bed reactor. So how did you solve that problem? Because most of the time it's floating.
So that's the point of how you steer your reactor. And from the peptides, we have decades in experience working with solid supports based also on polystyrene, and how we achieve a homogeneous mixture in our reactor. So that's not an issue for us.
So is that a commercial polystyrene bead which you're using?
Yeah.
NATO phase or?
For example, yes.
Okay.
We
All
are
right, thank
using
you.
what is available on the market.
Okay, appreciate it.
Very nice talk. I have a question about your new cycles. Are you adding any new step or removing any of the conventional steps like capping?
No. So overall, we are still applying the standard cycle for the
So you
solid
still
phase
do
synthesis.
capping?
We are just using another reagent cocktail for the detutelation, but there is no removal of any step or an additional step required.
And is your detutelation cocktail well tolerated? Is the detutelation time somehow limited, or can you run it for hours?
It will be limited at one time point, but we have also different mixtures available that we can apply depending on the issues that we observe during process optimization. I've just shown one example today.
Okay, thank you.
Very nice talk indeed. As the fragments get longer, I think you mentioned the 5-mer was the largest you've made. Is that right?
In the larger scale, so yeah, we used DNA and a short fragment just related to cost savings.
Sure. Well, the reason I ask is it's well established that as the oligo lengthens, DCA binds to the bases and
Yep.
it's retained to a large extent. I've always assumed that the mass transfer of DCA off the oligo was largely a function of a continuous flow of some very polar eluent that's capable of disrupting the hydrogen bonding right through the media. And I'm curious, when you have a stirred reactor like this, do you need a significant amount of acetonitrile or some other polar eluent to remove all of that acid that's bound to the oligo, of course, because you don't have this continuous flow through, right? And you'd see this more at larger fragments than you would in a smaller one.
Yeah.
So in a 20-mer, for example, it might be
So
problematic.
there are also other technologies for washing steps that you can apply to have a more efficient washing, and that's exactly what we are doing during the process development. So we start with our generic conditions, we see what we get there, and then that's exactly one of the topics that we are working on. So what's the washing procedure, what kind of solvents are used to have an efficient removal, while overall reducing the solvent consumption still for the overall manufacturing process. So that is always one part of the thorough optimization that we have to do for each specific sequence.
Right on, thank you. So related then, can you comment on, have you been able to apply this technology to something like a 20-mer or longer?
So far only on millimole scale, but we are working towards application on larger scale. So I've shown the preparation that's custom-made for that technology, and we have available already the equipment for the peptides that we have used for these scale-up experiments. But we haven't done so far really large-scale synthesis, but this will come shortly.
Yeah, excellent, thank you.
Hi, I also have the question about the detrioylation step. We know that the temperature of the detrioylation step sometimes matters. I wonder if you have explored the impact of different temperature on your detrioylation reaction?
In general, we can apply also temperature for our still bed technology. As mentioned before, we have equipment, especially for lab scale, where we can do that to evaluate also what is the optimal temperature for this process. But also here, I can't comment on any details at the moment.
Okay, thank you.
Nice talk. I would like to follow up on the solid support question. So do you observe any crush for your support during stirring? And is it because this method is used for peptide before, so is the property of the peptide resin is preferred, or actually after optimization is not necessary for the oligos?
So we are not observing any issues in this regard, but we are working also on that. We are not applying any peptide-related supports, so we are using still what is available on the market, polystyrene-based supports. It depends on how you set up mixing of your reactor, which kind of solvents you use, and so on.
Thank you.
Anyone stuck and they need the mic brought to them? Raise your hand, happy to run it over.
Okay, maybe I have one additional question. So, yeah, you mentioned like the detrioylation reaction, you have to extend the reaction time. Have you thought about like perform the detrioylation reaction by different cycles, like you perform it and wash it and perform it again, something like that, to shorten your reaction time?
Yes, so that's something that we evaluated, what is the best procedure in regards of applying one step, two steps, and so on, reaction times for that, washing step between cycles, and so on. But also here, I can't comment on any specific details.
Okay. May I ask, have you ever screened other scavenger in DODT to enhance the performance of the detrioylation step?
As mentioned before, I have just shown one cocktail. Yes, we have evaluated a lot of different reagents, including scavengers, but I can't comment on these details as we are still working on that.
Okay, thank you for your answer.
Hi, nice presentation. You might bring it up, I missed it, I just want to bring it up. I saw the polystyrene beads you showed. I'm not sure if you ever tried to CPG control the pore size glass beads. Is that even feasible or easy to break?
So we have never used this because you have some mechanical stress on the support, and that's not preferable to use than CPG with our technology, and especially we want to apply highly substituted supports, so then CPG is also not applicable, and therefore we are working only with polystyrene-based supports.
So, I mean, the answer is never tried, but
Yep.
I mean, have some idea about what's going to happen, right? All right, thank you.
Hi, nice talk. I have one quick question. Have you done any cost analysis on your approach when compared to the conventional analysis, and how much it is better than our current methods?
Yeah, sure. We have done calculations based on the current process that we have and compared it to the standard continuous flow synthesis. and we end up with a cost saving overall. That's also one of the drivers for that technology, talking to customers that requires large amounts of oligo APIs.
For your new debug solution, is it have the same restrictions that our normal DCA does with materials in, like you have to use Hastelloy, or is it similar in that, or is it less hard on any piping that you would have?
Our cocktails are less aggressive compared to the standard.
So like stainless steel, you have no problem with it?
No.
Okay, interesting, thank you.
Okay, no further questions. So thank you for listening.